I sent the class an email yesterday. I do that every Thursday, barring unforeseen circumstances. So please make sure you check your email if you have not already. It has relevant due dates, and it's good to know due dates. Okay. Again, I try to do this for you once a week, just so that we're all on the same page and that you have a place where it's like, okay, for this class, this is what's on, on the table. So I hope it's helpful and not too irritating. All right. So do you remember that we finished off class last time? I believe by establishing that awesome property of exponents. Okay, and I gave you the proof of why that was true. Again, you're never responsible for proving things in this class. I just like to show it to people in case they're interested, because it's good to know where formulas come from, right? Like when we get to the quadratic formula, remember x equals negative b plus or minus the square root of b squared minus 4ac over 2a. I'm going to derive that for you. I'm going to show you where it comes from because I think it lends meaning, because otherwise it's just like abstract gobbledygook nonsense. And then it doesn't have any meaning. Okay. So what I want to say is thus far with our logs, what we've established are as follows. A to the log base a of x is x. Log base a of a to the x is x. And when you take the log of something raised to a power, you can bring your exponent down in front. Now notice here, these values match. So you're just left with your exponent. We're not assuming they're the same here. Okay. These two happen precisely because they're inverse functions, right? You plug x in one function, plug it in the inverse, you get back to what you started. You take x, you plug it in one function, you take that output, plug it in your other, and you get back to where you started. Okay. So, one key thing to remember is whenever your exponent is unknown, you're gonna want to use logs to find it. Okay. We saw that we had to write this out. We have these to be equivalent, right? When we were trying to find the inverse function, we're like, oh gosh, we want to find our exponent. Okay. Well, the way you do is always using logs. So when your exponent is unknown, you're going to take logs. Okay. Now, in general, you're either going to take the log log, which is log base 10, nice, or you're going to use the natural log, which is log base e. The reason why those are the ones you use is because those are the ones that your calculator can compute. Okay. In general, it doesn't matter which one you use. I'm a natural log type of gal because, obviously one would hope I've gone through the calc sequence and I see the beauty of the natural log in E, and I love the number E. I think it's just beautiful. So I tend toward this, plus it's one less letter to write. And so my weary arm won't get as tired. There are certain situations where it's preferential to use one over the other. And that's precisely the situation when the base of your log matches the base of your exponent, because then you can use the fact that they're inverses and it's kind of a shortcut. Okay, I will show you. So this takes us all the way back to a problem that we posed sometime this week. Okay, remember we were looking at the population growing. We saw that it doubled. We saw that we started with 500. And we asked, when is the population 3,500? Right? This was the whole question, the question that motivated our whole conversation. Remember that? Ish. Okay, well, we saw, okay, we're looking for the exponent for when this is equal to 3,500. Well, what was the first thing that we would do? We would first get this alone. So we divided both sides by 500. 3,500 over 500 is 7. And we were trying to solve this. Are you ready? You're all going to sleep really well tonight because now you're going to know how to do it. What you're going to do is, my exponent is the unknown. So when your exponent is unknown, take the log. Okay, and then we're going to use this property. So check this out. You ready for coolness? Okay, so I have 7 is equal to 2 to the x. Doesn't matter whether you use the log log or natural log. I'll take the natural log. If we have equality, I can certainly take the log of both sides and maintain equality. Well, this is some number. Using this property here, what can I do to my exponent? Bring it down in front. We've released it. Can I get x alone now? Yeah. How do you undo what you're multiplying by? Divide. So I claim that you're going to have the natural log of 7 divided by the natural log of 2. Now, if you happen to use the log log here, that's totally cool. You would get log of 7 over log of 2. We call these the exact answer because we're not approximating using any sort of decimal. But if you're going to plug it into your calculator, that will give you a decimal approximation. So I have this calculator here today. So here I have ln of 7. Notice I close my parenthesis, divided by ln of 2. And I get about, rounded to 2 decimal places, 2.81. Notice if I used my log log and I did log log of 7 divided by log log of 2, I get the exact same thing. So to answer this long-standing question, in about 2.81 days, we'll have a population of 3,500. All righty. So some key steps. First thing you want to do is isolate your exponential. That's what I did here, first by dividing by 500. Take the log or natural log of both sides. Use my exponent property. It's not mine, but use our exponent property. And then solve for x using algebra. So what if I wanted to solve something like 3 to the x is equal to 23? I mean, in the back of my head, because I love to play with numbers, I know that 3 squared is 9, so 2 is too small. And 3 cubed is 27, so 3 is too big. Okay, so we got to get like the decimal between 2 and 3 that gets us there. Okay, so what do? Take a log of both sides. I'll just use my log log for absolutely no good reason. What do I do with my exponent? Down in front. So my left side becomes x times log of 3 equals log of 23. And how do I get x all by his lonesome? Divide both sides by the log of 3. So log of 23 divided by the log of 3. If you go a couple decimal places, you're going to get about 2.85. I did the computation. Now, you might ask, when do you use one over the other? LOG versus LN. If you have a base of E, use the LN because they're inverses and they undo each other. If you have a base of 10, use LOG log, again, because they're inverses. You can use the other one. You're just going to be working a little bit harder. Okay. Do you want me to show you? Okay. I'll do this twice. If I take the natural log of both sides, this is what I have. On my right, I have the natural log of 17. Check this out. Aren't these inverses of each other? Isn't ln of e to the 5x the same as log base e of e to the 5x? And since these match, what are we left with? 5x. What did I use? I used that property. When the base of your log matches the base of your exponent, they're inverses. Bye-bye. You get what you started with. Can I solve for x? Yep, divide both sides by 5. I know, it's that exciting, Ross.
I know.
Okay, so if I compute the natural log of 17, and then I divide that by 5, don't forget to close your parentheses, you're going to get about, let's go 2 decimal places, about 0.57. Now, you might ask, what would it look like if you took the LOG log? If I took the LOG log, first step, take the LOG log of both sides. Now, you wouldn't do both of these. I'm just showing you that you get to the same thing, depending upon whether you take one root or the other. Okay. Well, what can we do with our exponent? Bring it down in front. Notice these don't cancel because by default, this is log base 10. So I have 5x times the log of e equals the log of 17. But I just want x all by itself. So how do I get rid of what I'm multiplying by? Divide. So I need to get rid of a 5 times the log of e. If I do that, they cancel out on my left. And now what I'd compute is log of 17 divided by 5 times the log of e. Now notice when you put this in your calculator, a lot of calculators will make you put in an exponent. You would just put in e to the first. Make sure when you're plugging it in your calculator that you put parentheses around your entire denominator so that it knows the correct order of operations, right? Because otherwise it would do log of 17 divided by 5 and then take that whole shebang times log e. So what would that look like in a calculator? Do you want to see? If you don't, just don't watch. So we got log of 17. Now I'm going to hit divided by, I'm going to put parentheses around my denominator and I'm going to have 5 times the log. Now to get to e, I hit that second ln button. Notice it wants me to put in an exponent, so I'll put in a 1. And now I'll close my parentheses. And sure enough, we get the same thing. You with me there? Awesome. So one of the things that is so super crucial is to remember, you know, when things will cancel each other out. If you have the natural log of e squared, what's that equal to? 2, right? Because isn't this log base e of e squared? Those match, you're left with the exponent. What if I have the log of 10 to the 17th power? What's that equal to? 17. So you want to start noticing when those things match. You with me? So essentially, when you're solving a log, like say log base 2 of 8, what you're asking is what exponent do I need to raise 2 to in order to get 8. Okay, so whenever you're solving a log, you're looking for the exponent. Now let's do one a little more involved. If anyone has questions, just stop me. Like, I'm great talking about this stuff. It's so fun for me, but please let me know if I'm going too fast or if you have any questions. So what if I want to solve 3 to the 4x minus 5 power equals 38? Now, the first thing I note is I don't have a base of e or 10, so it doesn't really matter whether I do the log log or natural log. Okay, which log do you want to use? Log. Okay, I will take the log log of both sides. What was the beauty of taking the log of both sides? What can I do with my exponent? Bring it down in front. Whoa, notice you got a pretty complicated looking exponent. Put parentheses around it. Right, you're bringing the whole shebang down in front. All right, we want to solve for x. Well, lots of different ways we can do this, okay? One thing you could do is you could distribute your log 3 throughout your parentheses. And then chip away to get x alone. Another way to get x alone is first, couldn't we divide both sides by 3? Log 3, I mean. Because check it out, if I divide both sides by the log of 3, aren't I left with 4x minus 5 on my left side and then log 38 divided by log 3? What would be my next step for solving for x? We would add 5 to both sides. So now I have 4x is log 38 divided by log of 3 plus 5. Not there yet. What's my last step? We got to divide both sides by 4. So we get log of 38 divided by log of 3 plus 5, and that whole mess divided by 4. No one said it's pretty. Do you want to see how that would look in your calculator? Or do you all know how to? Yeah, okay. So what you would enter in your calculator is log 38 divided by log 3. I'm going to hit enter. Now I'm going to add 5, enter, divided by 4. We get about 2.08. Does anybody want to see me solve this where I would have distributed the log? Or would you all have divided by that naturally? You get the same thing. It's just different steps. You okay? Awesome. Awesome, awesome. Okay. So what if I want to solve this? 200 times 1.06 to the power of t is equal to 550. What would be my first step here? Good. First step, isolate the exponential. We would divide both sides by 200. So we would have 1.06 to the t is equal to whatever 550 over 200 is. I could care less right now. What's my second step? Take the log of both sides. What should we use? The LOG log or the natural log? LN, all right. We'll take the natural log of both sides. And if you're allergic to taking the natural log of both sides, you can always take the LOG. Kind of just kidding. Okay, what's the beautiful thing about doing that? Bring your exponent down in front. So we have t times the natural log of 1.06 is the natural log of this stuff. And then, as we said, use algebra to solve for, in this case, t. How would you get t all by its lonesome? Divide both sides by the natural log of 1.06. Be very conscious of your parentheses. And I'm going to do this computation precisely because I want you to see that we are going to get a number other than 2 point something, because that seems to be like this theme of the day. Okay, so the way we would do this is, notice here what I would do is I would take the natural log of 550 divided by 200. Now I close my parentheses. And then divide that by the natural log of 1.06. And we're going to get about 17.36. Yeah. Your online homework will tell you exactly what you want, what it wants done. And so will I. Usually I say you can leave exact answers or round to however many decimal places. I'll always let you know. Y'all with me here? Awesome. Okay. So before we move further into solving these things, I want to mention a few practical applications. Okay. we might as well see why in the heck are we doing any of this? Well, I really love gardening. And one of the things that's really important about growing food is the pH of your soil, especially when it comes to pesky blueberries. They're very, very particular. So one practical application that's used more in chemistry is the pH. And the pH, in case you don't know what it is, it measures the acidity of various liquids, essentially, that's related to the hydrogen ion concentration. Do any of you take chemistry? Took it? Oh, yeah. And not that you probably care about this, but it's measured in moles per liter. Moles per liter. Here's the formula. You don't have to know it. pH is negative log of H plus, and what's in here is your hydrogen ion concentration. Now, I don't have a base written for this log. What does that mean? Log base 10, good. Okay, so what would be a couple questions I could ask using this? Well, there's only a couple questions I could ask. I could give you the hydrogen ion concentration and ask you your pH, or I could give you the pH and ask you what your hydrogen ion concentration is. Right, there's only two unknowns. So let's do both ways just to be sure that we're all cool. Okay, so what is the pH if our hydrogen ion concentration is 0.001? Well, use your formula. We're looking for the pH. That's negative log, and we know this, it's 0.001. Now we could directly compute this in our calculator because it does the log log, right? You could say log 0.001 and then times -1. And so you're going to get 3. The other way around is a little more interesting if you're given the pH and want this. But first, let me ask, are there any questions here? Okay. So on the other hand, another question I could ask you is find the pH, or excuse me, find the hydrogen ion concentration if we have a pH of 6. Well, I plug this info in here. I have 6 is equal to negative log of what we're looking for. All right. First thing that I want to do is I want to note this is log base 10. We're going to need to know that. Just like before we would isolate our exponential, let's isolate our log. Do you agree the only way to isolate it is to get this negative out of here? How do you get rid of a negative? Multiply or divide by -1. This is our first log equation we're solving. Okay, when things are in the form of a log, we're pretty helpless. So this again is the mantra. change it to equivalent exponential form. Ready? How do we do that? You take, do you want me to write it here? Right, when you have it in this form, the way to change it to equivalent exponential form is you take the base of your log raised to that power, and that's what it's equal to. So what I have is 10 to the negative 6th power is my hydrogen ion concentration. As far as I'm concerned, you're done. But what 10 to the negative 6th power means is move your decimal point 6 places to the left. You okay? Let me know when you got this. Cool. All right. So there's one more little topic left to cover in this section. This is something that you do have online homework with. I tend not to go into this too much, but I think it's good. Okay. Let's start with something concrete though before we jump to it. So suppose I tell you that a sample of who cares what starts with 100 and grows by 10% each week. Can we write the equation of the exponential function that models this? Totally. In fact, this is really pretty sweet. What is my value of A? It's equal to 100. That's my initial value. Now I need to find my value of B. Notice B is growing, so it's 1 plus R. And in this case, R is 10%, so 0.1. So don't we have 1.1 to the X? You with me here? Isn't it kind of nice to kind of fold back to what we started with just to reinforce? Now, this is great. What I'm looking at here is a formula that takes into account my weekly growth rate. I could have done daily. I could have done yearly. Okay, I just chose a week. So the burning question is, what if I wanted to know what the continuous growth rate is instead of weekly? The thing you want to keep in mind is once you see continuous, that is our magic number E. Okay. So essentially what we're wanting to do is we're wanting to take an exponential function in this form, and we want to write it in the form of that. In other words, we want that base of E. So what I'm going to show you is how to bebop back and forth between forms. It's nothing you need to memorize. If for no other reason, you got a sheet of paper with notes. But it's a good thing to be able to convert back and forth. And I do believe you have some online homework in that. Well, first off, notice A is A. So nothing to do there, right? So what we need to look at is we need B to the X to be equal to E to the KX. Do you agree? If we're going to write these equivalently, this is what we need. Questions this far? Now, do you agree that I can rewrite my right-hand side as e to the x, or excuse me, e to the k raised to the x power? Right, because when you raise something to a power raised to another power, don't you multiply your exponents? Well, notice x and x match up. So don't we just need b to be equal to e to the k? All right. Now, what I want to say is as follows. We need b to be equal to e to the k. Sometimes we're going to be given one version, this sort of equation, and we want the continuous. Sometimes we're going to be given the continuous growth or decay, and we want the other. Okay, so what we need to do is we need to learn how to bebop back and forth. Okay, so e to the k equals b. In other words, if you're given a times b to the x and you want a e to the kx, notice what we need to find is k, don't we? Well, if I have b equals e to the k, how would I get to my b? Since b is e to the k, or excuse me, how do I get to my k? You take the log, natural log of both sides. What you do is you take the natural log of both sides, and doesn't that give us our value of k? So if you're starting in this form and you want that form, you take the natural log of b to find k. If you're starting in this form and want this form, what we see is that b is equal to e to the k. So all you do is compute e to the k to get b. Now, something that I want to mention is if you have a b to the x, a e to the kx, we know that if b is greater than 1, we have exponential growth. In those situations, your k is going to be a positive number. We know if b is between 0 and 1, we have dk. And what you're going to see then is that you're going to have a negative value for k. So when it's written in this form, you know whether it's growing or decaying by the sign of your exponent. So let's at least answer this question. Okay. Ready? We had y equals 100 times 1.1 to the power of x. And we want to write it as a e to the kx. Okay. So how do we do this? Notice we have it in this form. Let me get this sheet of paper back. We're starting in this form and we're going into that form. So we have our b, we want our k. To find k, you take the natural log of b. In other words, what I'm going to do is compute the natural log of 1.1. And I can do that. And I'm going to get about 0.09531. So written in continuous form, we would say that's 100 times e to the 0.09531. Now, what I want to point out is one particular thing, but I first want to make sure you're cool with the computations. I mean, literally to go from this form to this form, you take the natural log of this guy. To go from this form to the previous form, you just compute e raised to that power. Okay. But what I want to point out is when something had a weekly growth rate of 10%, that corresponds to a continuous growth of about 9.5%. And that makes sense because if something's growing continuously, it's going to grow faster, again, because you have it compounded on the compounding. So what if I have y equals 3 e to the 4x, and I want you to write that as a times b to the x? Well, we know a is 3. How do we find b? E to the 4th is equal to b. I'm going to do 0.4. It'll make our numbers better. So what I'm going to do is I'm going to compute e to the 0.4 power. And I get about 1.49. I'll go a couple decimal places. 1.4918. So in equivalent form, we would say this is 3, 1.4918 to the power of x. And just to make the comparison again, this had a continuous 40% growth rate. And I don't know whether this is, let's just say, an annual growth rate of about 49%. Great growth rate is great. So notice when you want to get equivalencies, the continuous is always going to be higher. The continuous is always going to be less than the weekly, daily, or annually, just simply because if you're trying to maintain that balance. All right, can I do one more example? Thanks. What if I have y equals 300 times 0.91 to the t? And I want to write that as y is a e to the kt. How do I get my value of k? K is equal to the natural log of b. You take the natural log of 0.91. You're going to get k to be about negative 0.0943. Notice I had a 9% decay rate, say annual, and then my continuous decay rate was 9.4%. Okay, one more. What if I have 20 e to the negative 0.45 t? And I want to write that as AB to the T. Do you agree this is telling me I have a continuous decay rate of 45%? How do I get my value of B? B is e to the K. In other words, we just compute e to the negative 0.45. And if you do that, you're going to get about 0.638. Now, we had a continuous decay rate of 45%. Just so that we're nimble with our exponential functions, what would be like my annual decay rate? Good, 36.2%, right? Remember, your B is 1 minus R. We have our B to be 0.638, and what we're looking for is what our decay rate is. Well, remember, to solve for R, you'd subtract 1. And then you want it to be positive. So what we see here is that a continuous decay rate of 45% is equivalent to an annual decay rate here of 36.2%. And my friends, we are done with 4.3. So I will assign the homework to be due a week from today, which I think is November 4th, right? Shazam, it's 2:50 on the nose. Have an awesome weekend.